We flip a switch and a room is instantly filled with light. We turn a key and this 2-ton machine just roars to life. We are literally surrounded by a force we can't see, but we absolutely cannot live without. Energy. It's the invisible engine that runs our entire world. But what happens when that engine just stops?
Okay, let's go back in time. Picture it. New York City, rush hour, November 9th, 1965. And then, all of a sudden, everything just dies. The lights blink out, the entire city, and a huge chunk of the Northeast is plunged into total darkness. This wasn't just some minor inconvenience. It was a massive wake-up call that showed everyone just how much we depend on a constant flow of electricity.
And the chaos? It was on an unbelievable human scale. We're talking about 25 million people spread across 80,000 square miles, all of them suddenly cut off, subways just frozen in their tunnels, elevators becoming these dark, silent traps. It was really the first time America got a good, hard look at how fragile our electrified lives really were.
So yeah, let's start right there, with the day the lights went out. That giant blackout is really our first big lesson. It's a powerful reminder of how deeply we rely on a stable, constant supply of energy just to get through the day.
So when you see what happens when it's gone, it really makes you stop and think, what is energy anyway? It's obviously more than just electricity coming out of a wall socket. It's something way more fundamental than that.
And its most basic level, energy is simply the ability to do work. But here's the really cool part. It comes in countless forms. You've got heat, light, motion, chemical energy, and its real power, its magic, is its ability to change, to shapeshift from one form into another.
And you can pretty much think of all energy as being in one of two states. So on one side, you have potential energy. That's stored up energy just waiting to be unleashed. Think about all that chemical energy that's locked inside a single lump of coal. Then on the other side, you have kinetic energy. That's the energy of motion. A train barreling down the tracks, that is pure kinetic energy right there.
Now here's where it gets really interesting. There's a fundamental rule in the universe called the first law of thermodynamics. And what it says is that you can't just create energy out of thin air, and you can't make it vanish either. You can only convert it. So that toaster on your counter, it doesn't use up electricity. It just transforms that electrical energy into thermal energy, heat, to toast your bread.
But of course, there's a catch. And that catch has a name. The second law of thermodynamics. It means that every single time you convert energy from one form to another, some of it gets lost as what we call waste heat. No energy transfer is ever 100% efficient. Some of it always escapes, without doing the job you wanted it to do.
So how inefficient are we talking about here? Well, have a look at this number. 15%. Any guesses what that might represent?
That's it. Only 15% of the chemical energy that's packed into a gallon of gas actually makes your car move forward. A mind-boggling 85% is just lost as waste heat, basically just warming up the engine and the air around you. So next time you're in a traffic jam, just think, it's a massive, inefficient cloud of wasted thermal energy.
Which, of course, brings us to a huge question. If we need all this energy, and using it is so darn inefficient, where on earth are we getting it all from? Well, for most of modern history, the answer has been a full-on feast of one specific type of fuel.
And that answer, by a long shot, is fossil fuels. We're talking about energy sources that were formed from the remains of ancient plants and animals buried and crushed over millions of years. And their dominance is just staggering. Somewhere between 85 and 90% of all the energy we use comes from the big three: petroleum, which is oil, natural gas, and coal.
Now, take a look at this chart. It shows you exactly how that dominance played out over the years. Look at the period right after World War II. Around the 1950s, you can see petroleum, that's the top dashed line, it just skyrockets right past coal to become America's #1 energy source. And, well, it's held that top spot ever since.
So, how do we even get this liquid gold in the first place? Well, as this illustration shows, it was a process that took millions and millions of years. Tiny little sea creatures and plants died, sank to the ocean floor, and got buried under layers and layers of sand and rock. Over eons, all that heat and pressure basically cooked their remains into the oil and gas we're drilling for today.
And getting to it, well, that's a whole other story. It's a massive technological feat. We use these huge oil derricks to drill down, sometimes miles deep, through solid rock, just to get to those ancient pockets of what is literally petroleum, which just means rock oil.
But here's something that might surprise you. When we refined a 42-gallon barrel of crude oil, we get so much more than just gasoline.
Sure, about 19 gallons become gasoline and another 10 become diesel. But the rest? It gets turned into jet fuel, asphalt for our roads, plastics for pretty much everything, even ingredients for your shampoo.
Now, all this incredible utility and versatility, it doesn't come for free. Our huge appetite for fossil fuels comes with a pretty serious environmental price tag.
Okay, so here's the basic problem. When you burn fossil fuels to release their energy, you also release gases. The main one is carbon dioxide, or CO2, which is what's known as a greenhouse gas. That just means it traps heat in our atmosphere. But here's the thing. Not all fossil fuels are created equal when it comes to emissions. This table compares the big three. If you look at that top row for carbon dioxide, you'll see that for the same amount of energy, natural gas emits about 117,000 pounds of CO2. Oil is worse, at 164,000. But coal is the highest by far, at 208,000 pounds.
Now, according to the source material we're looking at, a rise in these greenhouse gases contributes to a rise in global temperatures. And this has some very real effects, as you can see in these satellite images of the Arctic. On the left, you've got the ice cap in 1979, and on the right, what it looked like in 2007. The source points out that as temperatures go up, the ice melts, which in turn contributes to rising sea levels.
So all of this leads us to the biggest challenge of our time, really. How do we keep powering our modern world while managing these consequences? This means we have to start looking seriously at the future of energy.
This chart gives us a little snapshot of where things stood with renewable energy back in 2007. At the time, it was a pretty small, good, important slice of the pie, about 7%. And what's really interesting is how it broke down. More than half of that came from biomass, things like wood or biofuels, and another third came from good old hydroelectric power from dams.
And today, the options for renewable energy are becoming more and more diverse. We're talking about amazing technologies that can harness the power of the wind, the sun, the motion of water, the heat that's deep inside the Earth's core, and of course, developing new and advanced biofuels from all kinds of biomass.
But listen, powering our future isn't just about finding new sources of energy. It's also about simply using less. And there are two main ways we can do that. Energy conservation is all about our behavior. Simple stuff, like remembering to turn off the lights. Energy efficiency, on the other hand, is about technology, like swapping out an old light bulb for an LED that gives you the same amount of light for just a fraction of the energy. We absolutely need both.
When you get right down to it, from the laws of thermodynamics to the gas in our cars and the lights in our homes, we are all connected to this huge, invisible system. The choices that we make, both as individuals and as a society, are going to decide what that system looks like for generations to come. So this question, it isn't just for politicians or engineers, it's for every single one of us.